Hello, in this video I'm going to be writing an assembly language routine to multiply two 8-bit numbers together. This assembly program is going to be written for the Intel 8085 microprocessor, but the general idea is applicable to any processor that you may have. The Intel 8085, as you may know, is an 8-bit microprocessor. So each of the operands will be able to fit in one register, and the product, which will be a maximum of 2 bytes or 16 bits, will fit in a register pair, as you will see. So before we start writing the code, I'm going to start designating functions for each of the registers, and so let's go ahead and do that. So here are my registers. B will not be used for this one, and C will be a counter. It will be a bit counter. So it's going to basically be counting each of the bits as we shift them over, as you'll see in our main routine. D is the multiplicand. E is the multiplier. And H and L will be our result most significant byte and result least significant byte. Also higher order or lower order because there are only two in this register pair. So A, of course, will be our accumulator where we'll be doing our arithmetic and shift operations. And for this you need some sort of text editing program. I find Notepad++ to be very good, although the syntax highlighting and formatting is going to be a little bit different for .asm files because the ASM here is for x86 assembly, not this early 8-bit version. So what I'm going to begin by doing is initializing some of the stuff that we're going to be using. So initially we want remember, D is our multiplicand, so I'm just going to be putting a random value in here. Let's just try 8A in hexadecimal. Okay, and for our multiplier, which is register E, I'm going to be, let's just do 4, or how about C4 hex. And because it's a letter, we need to put a 0 in front of it. Okay, so that's the initialization that we're going to be doing. The main routine, which I'll just call mul, will be like this. I don't know if that's highlighted. I don't think this is highlighted. It shouldn't be. It won't matter because in our simulator, mul is not an instruction. But for the x86 it might be. I think it actually is. Okay. So for our mul, we need to initialize our product with 0 because we're going to be doing shifting and adding, and we can't do that if it's not initialized correctly. So the way I'm going to be doing this is moving into L00H and then moving from L to H. Notice that I could have done here instead I could have done LXI H 0000 hex, but this way saves a couple T states, which really doesn't matter, but oh well. And okay, and then so for our countdown, remember that's register C. I'm going to be putting 8 because there are 8 bits needed to be processed. Okay, so now we do mul 0. We begin by shifting the product area. Remember, this will be in a loop. So in our loop, we'll begin at mul 0. So the first thing we want to do is shift all the bits in the product area to the left, because when you multiply, every time you go to a higher bit, you have to shift to the left. And so the way we're going to do that is, first we're going to take L, and notice on the first one it doesn't really do anything because it's 0, but it will for each iteration after that, which is why we're doing this. And then I'm going to include this instruction. The purpose of this instruction is to clear the carry flag, because we don't want anything carrying into L when we shift it. Then we're going to rotate accumulator left. And notice I didn't use RLC because we're going to be using this carry into H, into the higher order. Because if there's a carry from bit 7 of L, we need that to carry into bit 0 of the higher order. Then we're going to restore L with the new value. Next thing we want to do is move H into there. Oops, there we go. And then rotate that, including the carry bit that we rotated from the lower order. After that, we restore that one with the new value. So this whole label here is just for rotating the product. Okay, now we take a look at the main mechanism for doing this multiply. So remember, D is the multiplicand and E is the multiplier. So the multiplier is going to be shifted, and whenever there's a 1 shifted out and we read that 1, we're going to add D to the product area. So the way we do this is, first we move from A into E, and now we're going to do RLC. It's not going to be RAL because we want to preserve whatever is in E. We don't want it to be carried away somehow. And also, RLC puts the value of the highest order bit into the carry flag. And why are we not rotating it to the right, you might ask? Well, because we start with the higher order, because when we shift the product area left, we want the highest order position to be first, to be shifted left. Okay, so we shift that, then we do move A back into E. Notice that after 8 iterations of this, E will be restored to whatever it was originally. So now the carry flag reflects bit 7. If the bit 7 is equal to 1, we want to add, otherwise we don't. So to do this, I'm going to put jump not carry to mul2. So what this will do is, if there's no carry, if the carry bit is 0, then it'll jump immediately to mul2, otherwise it'll execute the instructions that follow. If there's a carry out, then what we need to do is add the multiplicand to the product. So move from D to A and then add L. Remember, D is our multiplicand, so we want to add that and then add that to the lower order of the product. After that, we move A back into L. Oops. And then what we have to do is check if there's a carry out of the lower order. Remember, we're adding this to the whole 16 bits, so if there's a carry out, we need to increment the higher order. So again, we do something like this, jump not carry to mul2. There's no carry, there needs to be no further direction. If there's a carry, we just want to simply increment the higher order byte of the product. Mul2, so our final, here, let me make this a little bit easier to read here. Mul2 will be basically our counter refresh. So we're going to decrement the counter register. And in the case that it's 0, then we wanted to exit. Otherwise, we jump back to mul0. And then after that, we can basically do whatever we want. We can add whatever we want. But now I'm just going to be putting a halt instruction here to halt the program so we can look at the state of the registers to see if we got our answer correct. Okay, so I'm going to be going to save this, and now I'm going to open up a 8085 simulator so that we can execute this program and see if it worked. So I'm going to go here and go to my 8085 simulator IDE and running as administrator. Give it a second here to load up. So you can see our registers are here, our flag register is here, and the countdown, remember, will be in C, so you can watch that countdown, and you can see our product area grow as the program executes. One thing I'd like to bring attention to is that this is only 1 byte by 1 byte, but you can use this in an expansion to multiply operands of any size that you want. By using a similar process and adding the partial products to each other in the memory. So remember, in the memory you have a lot more space than just these registers. Well, there we go. Alright, so I'm going to be making a new file, and oops, I'm going to copy our program into the assembler. Ooh, that does not look good. Let me fix this real quick. Alright, now it looks a little better. And I'll assemble and load. And I'll call this multi-precision multiply. Alright, so now it's loaded up and we can go ahead and execute it. I'm going to be doing it at a fast speed. So you can see the countdown timer going down, you can see our address space growing. Remember, we started out with 8A and C4. You can see that E has been restored, and our product is 69A8. And you may confirm that for yourself, but other than that, that is all I have to show in this video. So I hope you enjoyed, and I hope you learned my thought process for making this, and I'll see you next time.